Floor is yours.
Thank you very much. Thank you for the kind introduction, and thank you for giving me the opportunity of talking here today of my work. So today I will talk about the work we have done on the strain-tunable spin wave propagation in a cobalt iron boron waveguide on a suspended piezoelectric MEMS bridge. This is the work that we have carried out within the MMMs project, and we have done it in Politecnico di Milano. I am a PhD student from the group of Professor Bertacco. So, we have seen that magnonics appears very promising for the implementation of radio frequency devices. Mostly, this is true when we are talking about passive devices and passive components, such as, for example, phase shifter, modulators, or also, for example, time delay units. Indeed, the technology that is being currently used has reached the limit when it comes to the possibility of enlarging the frequency range of operation and also of downscaling the dimensionality. Magnonics appears very promising in this respect because it allows at the same time a theoretical, very broad frequency range that goes between the megahertz and the terahertz, but also the possibility of scaling down and miniaturizing the devices. However, translating magnonics into commercial electronics is not trivial. Indeed, there are some challenges that we have to face. Some are a bit more easy, such as, for example, we need to define a well-defined magnetization in our system. Others are a bit more tricky to obtain, such as, for example, obtaining a way to control the magnetization or the internal field to be able to reconfigure our device. If we were in a lab, this would be very easy. We could just use an external electromagnet by changing the external field. However, it is difficult to miniaturize an electromagnet due to the power consumption and to the dimensionality. And therefore, different approaches and different solutions are required, which have to be miniaturized and on-chip. For example, when it comes to the definition of the magnetization, we could consider that we have, for example, a waveguide, and we want to magnetize it along its short axis to be in a de Moneshpa configuration to have an efficient excitation of a spin wave using an inductive antenna. This could be achieved with an on-chip approach with different solutions. One could be, for example, to grow our waveguide under the application of an external field. In this way, we are going to define a preferred directionality that is going to help us in maintaining the desired magnetization. Another possibility, that is the one that we saw in the previous talk, is to use some permanent micromagnets as an on-chip source of the magnetic field. Finally, we could also leverage the strain transfer from a substrate. So putting the waveguide on top of a substrate that induces a strain through an anisotropy. In this work that I'm going to present, we opted for the first solution that involves the use of the growth of a magnonic conduit under an applied field. Things get a bit more tricky when it comes to how to reconfigure these devices using a miniaturized solution. An approach could be, for example, using a micromagnet that is moving in close proximity. That is once again what we saw in the previous talk. However, I will now talk about the possibility of using a strain tuning. There are many works in literature that have shown how it is possible to tune the propagation of spin waves using strain. And some of them also demonstrated the possibility of having a voltage control tuning by putting a magnonic conduit on top of a piezoelectric material. Indeed, in this case, applying a voltage, we are going to contract or expand the piezoelectric film, and therefore we are going to change the internal strain, achieving a dynamic control. And this has been also used to realize some devices, such as, for example, interferometers. However, within the MMMs project, we tried a slightly different approach, that is integrating magnonic conduits on top of MEMS suspended structure. So in this case, we still have a voltage-controlled strain tuning, but we can also achieve a larger modulation because we are talking about a suspended structure, while still being completely compatible with an on-chip integration. So let me first describe a bit what MEMS are. MEMS stands for Micro Electromechanical Systems. They are mechanical structure that can be controlled electrically to achieve a movement at the micro or at the nanoscale. The fabrication is completely CMOS compatible, and this enables large-scale, low-cost production. We can just think about the fact that in our smartphones, we have dozens of MEMS. They are already very widespread in consumer electronics. They are used, for example, for motion sensing or as gyroscopes or even as microphones. So this is a very reliable technology that is already very widespread and very secure. Often, MEMS are integrated with piezoelectrics. A piezoelectric material is a material that, when it's subjected to a voltage variation, will tend to contract or to expand. So we can consider a very simple idea of a MEMS, in which we have a silicon membrane on which a piezoelectric material has been deposited with the top and bottom electrodes. If now we apply a voltage difference to the electrodes, we will have that the piezo will expand, and as a consequence, the structure will deform. Indeed, in this case, we are talking about a suspended structure. So the piezo is not fixed to a bulk. And this means that its contraction is going to lead to a much bigger effect, and therefore, in our case, also to a much bigger strain. These are the chips that we used in this work. They are MEMS provided kindly by STMicroelectronics within our collaboration, and they have a central suspended structure made of silicon, on which we have 4 PZT patches that share the same top and bottom electrodes. As you can see, there is a central part of the MEMS where we have a restriction, where the MEMS is thinner. And in this part, we basically have a thin, flexible silicon beam. If we now apply a voltage to this structure, we will cause it to bend upward. Indeed, here you can see the optical profilometer measurement taken on 2 different structures. One is not being actuated, while to the other one we apply the 20 volts. And as you can see, there is an out-of-plane movement which reaches a deflection of about 3 microns in the central part. We carried out also simulations using COMSOL multiphysics. First, we benchmarked the simulations that we did by comparing the displacement that we obtained with the ones that we experimentally measured. Then we used them to evaluate the strain tensor matrix. Here you can see the x-axis component, and it is interesting to note from the very beginning that the strain over the whole structure, which is shown here, is much stronger in the central restriction, where we have the central silicon beam. This means that this is going to be the best position for placing our strain-sensitive device. For this reason, this is the device that we fabricated. We placed a cobalt iron boron waveguide in the center, running through the restriction with a thickness of 40 nanometers. Moreover, we grew this waveguide using a sputtering machine in which we were applying on the system an external field during the growth. This was done to introduce an anisotropy that will keep our system magnetized in a de Moneshba configuration. Then we placed the antennas. We are using inductive antennas, and we placed them directly on top of the suspended structure. As you can see, they reach into the central part of the MEMS so that we will have a spin wave propagation from one antenna to the other, right in the part of the MEMS where we are going to have the highest strain. The contacts for the picoprobes were put, however, on the part of the chip where we have the bulk, so not on the suspended structure, because in this way we will be able to contact without damaging our system. To characterize the functionality and the properties of our device, we carried out some simulations. We started out using COMSOL multiphysics to extrapolate the strain tensor matrix over the waveguide. Here you can see all the different components being shown. Then we inserted this strain within an Ubermax simulation within the magnetoelastic term, which therefore will be spatially dependent. We also considered the presence of an anisotropy term to keep into account the presence of the anisotropy, which we induced during the growth to have the system magnetized in the Moneshba. We started with simulations in which we have an external field applied in the Moneshba configuration, the anisotropy but no strain. Here you can see the effective field and the magnetization. In both funnels, the top image shows the X component and the bottom one shows the Y component, which is the one directed along the short axis. As you can see, in this situation, we have a very well and uniform magnetic field, internal field, and magnetization along the y direction. However, if we now introduce the strain, the situation changes. Indeed, we can see that there is a reduction of the internal field in the central region that does not lead to a rotation of the magnetization, but does impact the spin wave propagation. To see this, we calculated the dispersion relation in the two cases, with the strain applied and without the strain applied. And what we saw is that the reduction of the internal field causes a lowering of the band toward the lower frequencies. And we also saw that this predicted shift is quite strong. We are passing from a ferromagnetic resonance of about 10 gigahertz to one of about 7, applying a voltage of 30 volts. So we are indeed shifting, we expect to shift quite a lot our spin waves propagation. Then we carried out measurements using a vector network analyzer. This is the image of the devices whose measurements I will show. We used meander antennas that were placed on the device with a center-to-center distance of 42 microns. Using the VNA, we collected the scattering matrix by making frequency sweeps between 4 megahertz and 40 gigahertz. I will mostly talk about the complex S21 parameter, that is the parameter associated to the transmission of the signal from port 1 to port 2. At first, we carried out a characterization of our device in the absence of the strain, so the MEMS is not being modulated. And in this case, we can see the classical spin wave signal of the imaginary part of the complex transmission parameter, where we can see that the spin waves appear as oscillations. And keep in mind that since the signal in our device was quite low, the measurements that I will show were all subtracted with respect to a reference that was taken in the absence of spin wave signal, and that therefore contains only electromagnetic noise. We also cleaned the sample more using a time gating procedure. At first, we characterized the functionality of our device by sweeping the external field. Here you can see the data taken between -80 and 80 millitesla. And we saw that, first of all, there is a well-defined propagation at 0 external field, which is the curve that you can see here, in between the 6.5 and 8 gigahertz. This means that having grown the waveguide in the presence of an applied field worked effectively in generating an internal anisotropy that is keeping the magnetization in our desired configuration. And we also confirmed this using micro-Moog measurements. Then we started to study the effect that the strain has on the modulation of spin waves. To do this, we made measurements without the presence of an external field, because this is the condition of functionality that we would like to have for our device. And we applied a voltage to the MEMS, inducing a strain. And the voltage was increased stepwise between different measurements. Here you can see the effect, increasing the strain between 0 volt and 12 volts. First of all, we can see that there is a shift in the spin wave band toward the lower frequencies, which is consistent with the variation of the internal field that we simulated. This variation also translates in a different phase accumulation at the output antenna. Indeed, if we consider as the relative phase variation with respect to a measurement taken when no strain is applied, which is the blue one, we can see that at 7 gigahertz, we have a phase shift of 700 degrees when the 12 volts are applied, which means that we are well above the 360 degrees that we would need for a device. Then we also tried to apply an even higher strain. We did this first with an external field. Here you can see the measurements for 25 millitesla applied. And what we saw is that at some point, we apply a strain that is so strong that we basically shift completely the band of the spin waves, so much so that it is not overlapping anymore with the one that we originally had when no strain was applied. This is not exactly what we would like to have for our device. And it is happening because even though we tried to put the antennas as far from the region in which we have the strongest strain modulation as possible, they are still in a place in which they are going to feel the strain modulation. So we are not just seeing an effect on the spin wave propagation, but also on the spin wave emission. However, from these measurements, we were also able to extract the variation of the internal field due to the magnetoelastic component, and it is about 1 millitesla per volt applied. We also noticed the emergence of some secondary modes. We are still investigating their presence, but we think that they are related to a rotation of the magnetization. Then we carried out the same measurements in the absence of an external field. And what we saw in this case is that when we increase the voltage applied, at first we see a shift in the band of the spin waves. But then at some point, around 20 volt, we see that the signal disappears. If we reduce back the voltage, we see that the signal appears back. And basically what we can see is that we can switch on and off the signal by changing the voltage applied in a completely reproducible way. This means that probably we are seeing the interplay between two energy terms, the anisotropy one and the magnetoelastic one. We carried out simulations to explain this phenomena. These are the ones taken for the absence of an external field, when no voltage is applied, and we are just considering the anisotropy contribution, which therefore is the strongest one in this configuration, and is keeping both the effective field and the magnetization oriented along the y direction. However, if we now apply a modulation of 20 volt, we can see that the magnetization and the effective field completely change. This is because the magnetoelastic component in this case is the strongest one. And it will cause the magnetization to break in the central part into different domains. And this will hinder strongly the spin wave propagation in accordance with the measurements that we did. Then we also studied how the dynamics of the MEMS can affect the spin wave propagation. To do this kind of measurements, we used again a vector network analyzer, but in a different way. We were using the so-called continuous wave mode. That is a modality in which we are exciting at a fixed frequency, and we are carrying out a measurement in time. The MEMS in this case is subjected to a DC offset to which an AC modulation is applied. Here are the measurements. You can see the absolute value and the phase of the complex S21 parameter measured in time. The measurements were done at 7.1 gigahertz in the absence of an external field. The red curve shows the measurement done when a voltage of 4 volts in DC is applied to the MEMS, but no AC is present. And as you can see, it is just a constant value throughout time. However, the situation changes if we apply an AC of 1 volt at 2 hertz. Now we can see that the signal starts oscillating with the same periodicity of the MEMS. And this is because we are modulating the strain within our system and therefore also modulating the spin wave propagation. We carried out these measurements using an AC modulation ranging between 0 and 5 volts. And what we could see was that we could achieve a dynamic variation of the phase of more than 400 degrees. We also repeated the same experiments at different frequencies, increasing it. Here you can see the measurement for a frequency of 1 kilohertz. And again, we can see that there is a modulation, which is always consistent with what we were expecting. But now there is also another aspect related to the dynamics of a suspended structure that we can exploit. Indeed, MEMS are suspended structures, so they will have resonant modes. And at resonance, even a small input will drive the signal to have very large oscillations and very large displacement. This is true for bridges, but it is also true for MEMS. So we simulated the different modes that we can expect to have in our system. There are both bending modes, so in which we will have an out-of-plane displacement, but also torsional modes in which we expect to have a rotation. We started characterizing the resonances of our system, and what we found out is that all the resonances are in the tens of kilohertz range. and that we can expect to have a quality factor estimated from the experimental lock-in measurement of about 100. This means that when we are applying a voltage at resonance, we expect to have a movement that is going to be 100 times bigger than the one that we would have if we applied the same voltage in a DC configuration. This means, in principle, that since we saw with our static measurements that at zero external field, we would achieve a 360-degree phase shift applying 8.5 volts, that in principle, we could achieve a full 2 pi rotation of the phase applying just 85 millivolt. We are still investigating this to prove it experimentally, but from the preliminary measurement, we did see that there is an impact of the resonance on the spin wave propagation. Another interesting aspect of the resonances is that, as you can see, the movement that the different resonant modes provide is very different. Here you can see the different displacements simulated, and it is quite different, the one that we get for the other modes with respect to the one that we get for the first bending mode, which means that also the strain profiles that we could obtain could be very different. For example, we could consider the fourth bending mode, and you see that the XX component of the strain, which is the strongest one in this case, is completely different from the left-hand side and the right-hand side of the MEMS. And this will lead to a very strange internal field, which basically is not symmetrical with respect to the center. And the corresponding spin wave propagation is a bit difficult to study because we are going to have completely different propagation on one side and on the other. Another mode that is very promising is the second torsional mode. In this case, we would expect to have a MEMS that is rotating around x-axis. In this case, the strongest strain component is an off-diagonal one. It is the XY component, which you see plotted here. And it is going to lead to an effect on the spin wave propagation, which is opposite to the one that we saw with the first bending modes and with the static measurement. That is, it's going to lead to an increase of the frequency with respect to the non-strain case. And therefore, this could be quite useful because we could modulate the frequency of our system in both directionalities, playing with the frequency of the excitation that we are giving to the MEMS. So, in conclusion, with this work, we have demonstrated the feasibility of integrating magnetic conduits on top of suspended MEMS structures. We have realized a completely self-standing device in which spin wave can propagate in the absence of an external field. And we have also demonstrated how we can tune the spin wave propagation, achieving a full 2 pi rotation using 8.5 volts. We have also started investigating the dynamics of the way in which we can dynamically change the spin wave propagation using the MEMS actuation. And in particular, we have seen that we can change the strain in a dynamic way, and that we have some interesting perspective for the future for achieving very low voltage control of the spin wave propagation, and also achieving different strain profiles using the different modes. With this, I would like to thank all of my colleagues and my supervisor, with a special mention to the work done by Antonio Angotti. And most of all, I would like to thank all of you for your kind attention.
So thank you very much for a very nice presentation. And now the session is open to questions.
Thanks for the nice talk. I have a question. Is it very difficult to image this spin wave propagation in such devices?
Okay, so imaging it using, for example, a vector network analyzer, so an all-electrical measurement is not so difficult because the contacts are on the bulk part, so they are not moving, and therefore it is quite easy. When it comes to measurements done optically, for example, we carried out some micro-mock experiments, then it is a bit tricky because when the MEMS move, we have to adjust the focus. We also would like to carry out in the future some time resolved mock measurements, and in this case, we are going to use like the static approach. So we are going to deflect the MEMS, take the measurement, deflect it again, and take another measurement.
And also it takes a lot of time for optical measurements to perform.
It depends also on the time scale, I guess. Yep. We could also try to make it in such a way in which we have a good synchronization and we always take the image in the right moment, but I would think that it's a bit hard. But our approach is more device-oriented, and we are more interested in the all electrical characterization rather than, like, the optical one is very interesting for us to actually understand how the device works.
Thank you.
Yeah.
Thank you for the very nice talk. Very impressive. Looks very cool. I had a question because do you also actually take into account the curvature? Not only for the strain, but also really for like the magnetic order.
So far, we didn't because the MEMS is basically 1 millimeter long and it is deflecting of 3 microns. So the curvature, I used like these images with a very big curvature to give the idea, but it's actually a second order effect. I think that at some point we might want to introduce it also mostly in our simulations, but as a first order, it's not so relevant.
Thank you for your nice talk. At one point, you were discussing the peak in the S21 spectra, which you were not able to explain, or you were explaining it with another spin wave mode. I was wondering if you consider also that it could be higher order mode of the meander antenna.
Yes, but we would have seen it also when we were doing the characterization with the field. Like if we consider now the same, we characterize first the device without any strain. And in that case, we never see the emergence of secondary modes.
Okay.
We see them only when the strain is applied. What we would like to do now is to make some micro-Mach measurements with the strain applied to actually see if the magnetization is tilting, because the simulations tell us that at the border, there might be some more, like some stronger tilt that might lead to the formation of stronger edge effects.
Okay, thank you.
Thanks a lot for the great talk. Did I get it right that the main application you have in mind is RF filters beyond 6G? Is this correct?
Yes.
Okay.
Like we are quite far still from that results, mostly because these devices do not yet have a very good throughput of power. But this was like we showed that this is possible. So
okay,
yes.
Thanks.
Are there any more questions? So if no, I have one question, maybe also connected to the strange emergence of the mode. Have you considered influence of the strain on the phononic modes, on the acoustic waves, and possible hybridization with Magnon?
We are considering this, but in that case, the measurement was done when the MEMS was static. So we do not think that there was this kind of interaction. We would like also to play with the monon-phonon scattering, but to do this, we would need some frequencies that actuate the MEMS in the gigahertz to be in the same frequency range, more or less. And this would be quite tricky because we would need the MEMS structure that have resonances in that order of magnitude, which would need going to nanoscale devices, which is, from the fabrication point of view is not so easy.
My question was more like that you shift the acoustic dispersion in a way that it will cross the Magnon dispersion, and thus these two dispersions will hybridize, and you might see this in your signal.
We could investigate this. Actually, it's quite interesting idea. We didn't think about it and we didn't look it out, but we will surely do.
Okay, so let's thank the speaker again. And the next talk will be